is about hybrid techniques and understanding about different kinds of technology, but in this case it's CPAIOR for quantum computing, and I think a lot of us are going to be learning about quantum pretty much for the first time. So we're really looking forward to these three talks. And the first talk is from David Bernal, who'll be giving it on integer programming techniques for minor embedding in quantum annealers.
Hello, my name is David Bernal, and together with Kyle Booth, Raouf Dridi, Hedayat Alghassi, Sridhar, Tayur, and Davide Venturelli, we want to present our work on integer programming techniques for minor embedding in quantum annealers from Carnegie Mellon University and NASA US Array. So our goal here is to improve the quality of embedding methods using integer programming. The state of the art currently deals with heuristic methods, which are fast, but they don't provide guarantees of solution and are not deterministic. Challenges here is that we're dealing with an empty hard problem. This should be done as fast as possible because it can be counted as a pre-processing step before actually performing the quantum annealing, and the different results in the embedding actually yield different performances in the annealing. So the approach here is that we're going to use linear integer programming in order to formulate this model, and then we're going to apply a decomposition approach to solve it more efficiently. As the first talk in the quantum computing session of this meeting, the other talks talking also about quantum annealing. Let me tell you about the machine. So it's this big black box, right, which is mainly there to isolate a chip. Here we have this inverted wedding cake, which is basically dropping the temperature to 15 millikelvin such that the quantum computer, that chip, is working at that low temperature and really isolated from the world. Now, inside of the chip, what we will find are these teeny tiny cells where we will find in each one of them 4 vertical and 4 horizontal metal loops, which are going to be used in order to represent the qubits by just in low temperature making current flow clockwise or counterclockwise. You can represent pluses and minus ones. So you can represent this graphically as this figure over here, where you see that the blue tiles are just couplers that allow you to model interaction between the different qubits. And in another graphical representation, you have this so-called chimera tile, where you have the red edges being the qubits, and the red nodes being the qubits, and the blue edges being the couplers. So this quantum annealer, it minimizes the energy of an Ising spin problem, but those interactions of the Ising problem need to lie on a graph limited by the hardware. And then we get all these chimera and this chimera architecture, right? So the quantum computer that is available at NASA Quantum AI Laboratory has this 16 by 16 imperfect chimera graph hardware. And imperfect because it's highly complicated to get these machines to work, so some of the qubits are just faulty, right? The next generation of these chips are going to have this so-called Pegasus graphs, which are a little bit more involved. So if you want to solve an arbitrary Ising problem in these quantum annealers, you need to minor embed the graph describing your problem into the graph of the hardware. So what is this minor embedding? There are basically 3 conditions. Every original variable from your problem graph needs to appear in the hardware graph. Each node in the hardware graph or qubit can only represent 1 variable of your original problem. And if there is an edge in your original problem, it better show up in the representation of the hardware. So an example is embedding this triangle into a square, where you can see that in order to model this triangle inside of this square chip, you would need to duplicate, basically create this logical variable into 2 qubits. So this is exactly what we're looking for. Now, besides these conditions, we have other desirable properties. We would like to have, for example, the smallest possible embedding, given that there are some size limitations in the problems that we can solve. Or, for example, reduce the length of the so-called chains, which are just the number of qubits that represent a single variable, because the longer they are, the more prone they are to break, meaning that after performing the annealing, those qubits end up having different values, although they are supposed to represent the same value. So how is this problem solved? Through a heuristic proposed in 2014. Basically, you're going to iteratively construct these vertex models, which are just the mappings of the problem variables into your hardware. And how do you do that? Let's say for this example, you just randomly assign the nodes in your hardware, and then you start joining the edges by shortest weighted paths, where the weights are given for assignment or unassigned nodes. So here you can see that these 2 edges are trivial to define, and this purple edge between orange and green, well, how can you model this? You just extend the vertex models, meaning that what you're going to do is that this node is now going to represent green too, right? So how may this fail? You see, when we're randomly assigning this, in this particular example, what if it randomly went this way? You can assign certain edges, but some other, in this case, the purple one between orange and green, the only path goes across a qubit that has already been assigned. So the heuristic will fail in this case, right? So, for instance, the heuristic failing doesn't guarantee that the embedding is non-existent, and this is a challenge that we want to overcome. So our quantum computing group back in 2018 proposed a computational algebraic geometry approach to this problem, which basically, instead of looking at the mapping between logical and graphical to graphical hardware graph, it goes the other way around. It finds a system of polynomial equations, all turning around some binary variables, which basically say whether a node in the problem is mapped to a certain qubit in the hardware, right? And then the system of polynomial equations, where you encode all the conditions that define an embedding through a Grosvenor basis computation, you can compute the algebraic variety. And by that, we mean all the possible solutions of the embedding, right? So for this tiny example that I just showed you, the number of possible ways of embedding these graphs is 48. So now this approach, the one that we're proposing here, is through integer programming methods. And here what we want to do is encode these conditions inside of linear inequalities in terms of the same binary variables that were defined earlier. And we're going to solve this through integer programming. So we're only interested in a single solution instead of the whole variety, as in the computational and as in the algebraic geometry approach. And here we are going to use the feasibility of the integer program as a valid proof of existence of the embedding, and the optimality bounds as objective bounds for a given objective that we can define as these key properties that we were talking about. We implemented this in PyIOR, which is an open source Python package, which allows you to use commercial and open source MILP solvers. So this is the model that we're presenting. I'll go quickly through it, but basically it says that the embedding must be bounded by the sizes of the graphs that are given. Two variables cannot be mapped to the same qubit. The number of qubits, you can define a priori a size of those chains, and given that you can bound the size of the vertex models and only look at qubits that are within that distance. And then the two complicating parts are, first, making sure that the vertex models are connected. We call that the fiber condition. And whether the edges appearing in the original problem are going to be appearing in the hardware implementation. So these two conditions, we can still model them as linear programs, but then these are a little bit more complicated, right? Because then we are inducing an exponential number of constraints, for example. But if you were able to find alphas, gammas, and deltas that satisfy this set of linear inequalities, you would be able to find an embedding, right? And then if we define an objective function in terms of those variables, now we can encode everything as an integer program. And minimizing size is an example, but there are many more that can be defined this way. So the current integer programming model that I just showed comes from the linearization of that polynomial ideal from the computational algebraic model. So we also wanted to address this problem from a new stance. And what we wanted to do in this case was using a master problem and an algorithmic generation of the constraints. So the two complicating parts that we were talking about, those exponential number of constraints in order to model the connectivity within the vertex models, that we can address just by constraint generation and only adding those constraints that are relevant for our problem. And then the other complicating part, which had to do with these edges in the original problem being edges in the graph, those we can encode with a new variable and then use that in order to make our solution process more efficient. So here, an illustrative example just to begin. We want to embed the source graph into two cells of Chimera. You can see that this is very trivial. Just we need to add an extra embedding here. This is challenging for the heuristic. It will fail 50% of the time. Now, when you solve it with the computational algebraic approach, this is a slightly bigger problem. It just, after 5 hours, runs out of memory. On the other side, with the IP approach, we're able to solve this efficiently, in particular with commercial solvers such as Gurobi and Sequence, where we are able to find and guarantee optimal solutions in less than a minute, right? Our decomposition approach is actually even more efficient to find a good feasible solution, but it takes some time to guarantee optimality. Now, generalizing that example that we had, we're going to generate 80 instances just by randomly assigning probabilities to these edges of existing and then collapsing from 0 to 3 of these edges just to make sure that these are possible to embed into Chimera embeddings. And here we show the following graphs. So in this axis, we have all the experiments, 2 cells Chimera, 4 cells Chimera, with 0, 1, 2, and 3 edges being collapsed. We see these box plots are 1,000 runs of the heuristic. And here we see the runtime of, in red, you're going to have the decomposition approach. In yellow, you're going to have the monolithic approach. The circles are going to be just finding a feasible solution, while the triangles is going to be minimizing the size. So from this, you can see that we're still 1 or 2 orders of magnitude lower than the heuristic. But I would like you to pay attention to the plot on the right, which compares the number of qubits obtained on the y-axis by our integer programming methods versus the heuristic. And there is an extra piece of information, which is the size of the marker. The bigger the marker, the more times the heuristic fails. So in this particular example, the heuristic is failing more than 50% of the time. No, sorry, for more than 50% of the instances is failing more than 50% of the time, right? And then our methods, we're able to find a feasible solution in less than 20 seconds for all of these examples, right? And prove optimality in less than 5 minutes for 94% of these examples. Now, for truly random graphs, or those rangy graphs varying in size from 1 to 35, in probabilities of the edges from 0.1 to 0.7, generating 5 instances each and trying to embed them into 1, 2, 3, and 4 cells of Chimera, 1 or 4 cells of Pegasus, we end up with a large computational study with more than 2,000 instances that we're solving here. In these plots, we're only comparing the decomposition method versus the monolithic method. And we see on the x-axis, the decomposition method, on the y-axis, the monolithic method. For this is the time to find a feasible solution. Here we have the size when we're minimizing the size of the embedding and the time to minimize the embedding. So basically everything above the diagonal is better for the decomposition, below the diagonal is better for the monolithic approach. And we see, for example, that for most cases, the decomposition approach works better. Just in certain cases, that is really hard. For example, for the heuristic, which are larger instances, having all the problem at once helps the MILP solver to prove infeasibility in some cases. So some applications. In the literature, somebody wanted to embed these graphs into one cell of Chimera and Pegasus, claiming that Pegasus was way better. They achieved to do that with the qubit gadgets, with the first row of this in a single cell of Chimera and Pegasus. With the second row, they were claiming that with Pegasus, you only needed one cell, while with Chimera, you needed more. And in their results, they would show these 3 embeddings for 3 of those gadgets. In our case, when we run our methods in less than 10 seconds, we were able to reduce these 2 large embeddings into a single cell of Chimera. And this other one, we were able actually to prove that it was the optimum. Another application, for example, is protein folding. This was back in 2012, the largest problem that was ever solved on a D-Wave machine, and it was just limited by the size of the chip itself. Back then, it was a 4x4 chip, very faulty, as you can see. And then we use this as an initialization in order to find a better embedding through our integer programming methods. And we're able to reduce the qubit footprint by almost 9%, so which is relevant for this case. So here, what we did, we developed these monolithic integer programs derived from polynomial equations, and then we came up with a decomposition method in order to address this problem more efficiently. So we implemented these methods and tested them with a large computational experiment. We saw how we tried with target graphs, which are designed for the D-Wave quantum annealer. And although we're slower than the heuristic, I won't claim otherwise, we are able to use to our advantage these rigorous methods, for example, proof infeasibility and optimality bounds, in order to get better information out of these embeddings. This might be useful, for example, for applications where you are going to be running basically the same kind of a structure of model over and over again. So you might as well pay it forward and spend some time in the embedding before. So finally, we showed some applications, some gadget embeddings. For the sake of time, I skipped some spanning tree problems for communication, but they're on the paper. Protein folding, and promising future direction is taking advantage of symmetries that appear in the target graphs. We will lose generality by not addressing any graph, but we can gain a lot in terms of performance. Thank you, and if you have any questions, please let me know.
Thanks, David. That was blindingly
exciting.
I don't see any questions on the chat. Has anybody got any questions from the people? We're a bit short of time, so just one question probably. This one. I could ask one. So when I looked at the model, it seemed to me that a lot of the constraints were actually logical constraints rather than numerical constraints. And I was wondering if CP couldn't be really useful here, or some hybrid of CP and IP.
Indeed, actually, that's something that we were considering at the beginning. As you can notice, I don't speak that fast. Second, definitely we could also see at the solution process of using an IP solver that many of these were sort of killed by the pre-processing in the IP solver. So that only showed that a CP-oriented solution method would work well. That is among the future work that we want to do. On the other hand, we also wanted to emphasize that having this objective function, sometimes finding a single embedding is good and useful, but the heuristic is really good at finding that embedding. So at least finding some embedding. So maybe we wanted to focus more on the optimization side of things. But yeah, definitely. I mean, I think that if you work on CP and want to address a really cool problem, this should be something that you should be looking at.
Great. Well, thanks very much, David. That was really interesting. And we better move on to the next talk. So we're already a bit late. And this is Eldan Cohen, who's going to present a talk on an Ising framework for constrained clustering on special purpose hardware.
Hello, my name is Eldan Cohen, and I am presenting our work, an Ising framework for constrained clustering on special purpose hardware. This is a joint work with Arik Senderovich and Beck at the University of Toronto. In recent years, we see the emergence of novel computation platforms, such as adiabatic and gate-based quantum computers, the digital and CMOS annealers, etc. These platforms are capable of solving combinatorial optimization problems in hardware, and several of these platforms have adopted the Ising model as their mathematical formulation. Constrained clustering is a core problem in data mining. It has received significant attention over the last 2 decades, and different algorithms that support different types of constraints have been proposed. The research question that we investigate in this work is, can we use special purpose hardware to solve constrained clustering problems? The problem of constrained clustering consists of using small amount of labeled data in the form of constraints to improve the clustering performance. Constrained clustering allows to exploit site information and domain knowledge and is a form of semi-supervised learning. In our work, we consider 2 well-known types of constraints: instant level pairwise constraint and partition level constraints. Instant level pairwise constraints are either must link or cannot link constraints that state that a pair of data points must be placed in the same cluster or alternatively cannot be placed in the same cluster. Partition level constraints are simply cluster labels for a small portion of the data points. Consider the following example for clustering with constraints. We are given a set of 2-dimensional data points and we are asked to cluster the dataset into 2 clusters. It is not clear if it is better to use 2 horizontal clusters or 2 vertical clusters. Now imagine we are given the following constraints: 2 must link constraints and 1 cannot link constraint. In this scenario, it is clear that the best solution is to use 2 vertical clusters. Now, I will formally define the problem. A constrained clustering problem consists of a set of data points x, the number of clusters k, a set of must link constraints m, a set of cannot link constraints c, and k sets of partition level constraints that correspond to the k clusters. The goal is to find a partition of the data points into k disjoint subsets S1 to Sk that minimizes the within cluster pairwise dissimilarities while satisfying the must link constraints, the cannot link constraints, and the partition level constraints. In this work, we present 2 Ising models for the constrained clustering problem. A general model for clustering into k clusters that I will present in this talk, and in the paper we have a compact model for the special case of 2 clusters. Recall that our goal is to investigate the use of new special-purpose hardware for solving the constrained clustering problem. In our work, we solve our Ising models on the Fujitsu digital annealer, the DA, which is a specialized CMOS hardware for solving Ising optimization problems. The DA algorithm is based on simulated annealing. However, it takes advantage of massive parallelization and has a specialized mechanism to escape local minima. Before presenting our Ising model for constraint clustering, I will briefly describe what Ising models are. Ising models consist of a set of variables that take the value -1 or 1, a set of pairwise couplers, and a set of biases, and the goal is to minimize the following quadratic energy function. A closely related model is QUBO, quadratic unconstrained binary optimization. The main difference is that the variables are binary variables that take the value 0 or 1. We can easily convert QUBO model to Ising model, and we use QUBO to model the constraint clustering problem. Here we show our QUBO model for constraint clustering. Our decision variables are Qik that are equal to 1 if data point I is placed in cluster K. The first term in our energy function corresponds to our objective of minimizing the within-cluster pairwise dissimilarities. The second term is a penalty term that enforces that each data point is placed in exactly one cluster. The following terms are penalty terms that enforce that the obtained solution satisfies the must-link constraints, the cannot-link constraints, and the partition-level constraints. Each one of these terms penalizes the objective with a given penalty weight for a violation of the corresponding constraint. In the paper, we discuss the choice of the penalty weights. We empirically evaluate our approach on 8 benchmark datasets. We compare our Ising framework solved on the DA to state-of-the-art heuristic methods including MPCK-means, LCVQE, and PLCC. We also compare our approach to an exact constraint programming model and CPU baselines. In our evaluation, we use the metrics adjusted rand index, ARI, normalized mutual information, NMI, and the percent of violated constraint in the obtained solution. Here we compare our Ising framework solved on the DA with the heuristic methods on problems that involve instance-level pairwise constraints. We vary the number of pairwise constraints in the range 50 to 500. We generate 50 random instances for each number of constraints, and we measure the mean adjusted rand index, where higher is better. We can see that in all cases but one, our framework is as good and usually significantly better across all number of constraints. In the paper, we present results for the other evaluation metrics and for partition-level constraints. One advantage of our Ising framework is the ability to combine different types of constraints without the need to create a specialized algorithm. The two heat maps show the results for combining different types of constraints in 2 benchmark datasets. On the x-axis, we have the fraction of partition-level constraints, and on the y-axis, we have the number of pairwise constraints. The color indicates the mean ARI, and recall that higher ARI is better. We can see that fusing different types of site information can improve the clustering performance. Next, we compare our approach of Ising models solved on the DA with a constraint programming approach with similar objective solved by GE code. We set a runtime limit of 5 seconds for the DA and 500 seconds for CP. We evaluate the obtained solutions based on their objective value, the ARI, and we also measure the percent of solution proved optimal by CP. We can see that solutions found by our framework in 5 seconds are approximately equal or better than solutions found by CP in 500 seconds across all configurations. We can also see that CP was unable to prove optimality of instances in most configurations. To summarize, we present an Ising framework for constraint clustering on special purpose hardware with pairwise and partition level constraints. We demonstrate the framework's performance on a specialized CMOS hardware, the Fujitsu digital annealer, and show that it outperforms state-of-the-art heuristic methods. We also show that it can seamlessly solve problems that involve both pairwise and partition level constraints, and that it produces a solution approximately equal or better compared to a CP model in order of magnitude faster runtime. In the paper, we present a compact Ising model for the special case of 2 clusters, and we also discuss practical challenges in embedding our model on special purpose hardware. Thank you for listening. I am happy to answer questions.
Thanks, Eldan. I don't know if anybody wants to switch off their silence and ask a question. So I can do, we've got a bit of time. I was curious about this one hot requirement that actually at each point is only assigned to one cluster. And you talk about finding a value for lambda or to ensure that takes place. How can you be sure about that? I mean, otherwise it's you soften all the constraints.
So in the paper, we actually have a proof for a value that if you increase, so that beyond this value, the optimal solution is guaranteed to satisfy this, but it doesn't mean that a heuristic solution is guaranteed to find it. But the value that we choose that is high enough was found to satisfy the one hot constraint in literally all the instances that we use. But I mean, as a heuristic method, it can not find it. We just guarantee that the optimal solution, had it been solved optimally, would satisfy it.
Would, yeah. So Tommaso early asks, is the Fujitsu annealer only a parallelized simulated annealing machine?
So it is a classical hardware. It does several things. There's actually a paper that describes, I guess, not everything because it is a commercial product, but the main component of it. So we have a reference in our paper. But it is a classical hardware that is informed by some quantum ideas and principle, and it is using massive parallelization and a core algorithm of simulated annealing. So I don't know if this is everything. I mean, some of it is the commercial product, but in the core of it, it does some sort of simulated annealing, and it uses parallelization. And it is specialized to solve this type of Ising optimization problems.
I guess the corollary question from Tommaso, how much of the increased performance is because of the model and how much is because of the parallelism?
Oh, so that's a good question. It is good because we actually talk about it in the paper. So we actually compare, the same model, this Cubo model solved on the Fujitsu digital annealer, and we compare it with a classical Cubo solver, a simulator. Actually, 2 of them. One is a taboo-based, and one is a just classical simulated annealing, and we outperform the classical solutions. So we give 5 seconds to the Fujitsu, we give 30 seconds to the classical solvers, and we still find better solutions, which means we get more than 6 times speed up for this on average.
All right. Well, thanks very much, Eldan.
Thank you.
It was a very good talk. So the third talk and the last talk of the session is from Yuchen Pang. on the potential of quantum annealing for rapid solution structure identification.
Hi everyone, my name is Yuchen, and in this talk, I will introduce our paper, The Potential of Quantum Annealing for Rapid Solution Structure Identification. Firstly, what is quantum annealing? Simply speaking, quantum annealing is a method to find near-optimal solutions of classical Ising models, which is an optimization problem that's defined like this. Specifically, quantum annealing solves this problem by building analog quantum device. And there are some reasons for doing so. Intuitively, a classical system can only represent one configuration at one time. However, a quantum system can simultaneously represent multiple configurations. This would lead to non-classical behavior and an interesting question. Would quantum annealing faster than classical solvers? So why do we study quantum annealing? As I have just mentioned, quantum annealing uses some non-classical techniques based on physics, and this might lead to novel algorithms. Also, Ising model itself is an interesting problem in the sense that it's hard and many other interesting problems can be reduced to it. Moreover, there's a company called D-Wave System that has been improving the hardware for many years, and at this moment we have access to machines with 2000 qubits, which means 2000 variables, and very soon we will have machines with 5000 qubits. Before getting to the main results, I want to say a few more words on Ising models. Here I have the objective function of Ising model H sigma, and let's firstly look into a specific quadratic term -1 times sigma 1, sigma 2. If we represent these two variables as two nodes in a graph, we can connect these two nodes with a colored H, and the color would represent the coefficient -1. Note that this negative coefficient indicates that this term is minimized when these two variables are equal. Similarly, if the coefficient is positive, the term would be minimized when these two variables are different. Using the same rule, we can represent the linear terms in the objective function as colored nodes, and putting this together, the whole objective function can be represented as a colored graph, and this tool would be useful to understand the Ising models we are. So the actual Ising model we can solve directly using the hardware have some limitations. Firstly, the corresponding graph has to be given by the hardware topology. For the hardware we are using, the graph is a 16 by 16 chimera graph. As you can see in the figure, this graph contains 16 by 16 cells connecting to their neighbors, and each cell is a bipartite graph with 8 nodes. Moreover, some nodes in the graph are disabled because of hardware defects. Also, the hardware only supports coefficients J and H in specific ranges with some precision limits. This also limits the problems we can solve using the hardware. In this work, we select 7 algorithms for comparison. 3 of these algorithms are state-of-art, so we use them for benchmarking, while the other 4 provide intuition and breadth. In the complete search category, we choose integer quadratic programming and linear programming using Groovy. For local search, we compare Monte Carlo Markov chain, message passing, greedy algorithms, and a large neighborhood search algorithm called HFS. This algorithm is designed specifically for the hardware topology we are using. For quantum annealing, we are using a D-Wave 2000Q machine to perform the experiments. The workflow of our experiment looks like this. Firstly, according to the hardware topology, we generate 100 random instances of the problem. Then, we solve these problems using different algorithms, and finally, The first problem class we looked at is biased ferromagnet, BFM. In BFM, we set all J values to -1, which makes all variables tend to be the same. Here I have an illustration of the energy landscape of BFM. And as you can see, all 1s and all -1s configuration gives local minimum. Note that these two configurations are far away in the sense that you have to flip all assignments to convert one from each other. Then we set most H values to 0, but a few to be -1, so the whole system is biased towards the all ones configuration. So imagine if a local search algorithm gets stuck in the all -1s configuration, it would be very hard for it to get out because you have to go very far to see the other direction is actually better. Then we try to solve the BFM problems using the 7 algorithms that I have just mentioned, and here are the results. In these two plots, the x-axis is the runtime in log scale, and the y-axis is the optimality gap. These two plots show the same data, but the right figure is a zoomed version of the lower portion of the first figure. The first conclusion we got from the results is that BFM is easy for quantum annealing. As you can see, the green line almost immediately finds the solution at the beginning. However, this problem is also easy for complete search. The blue and purple dots also immediately find the solution at the first iteration. This is because the problem is so well structured and the complete search algorithm can automatically detect that. On the other hand, this problem is hard for the large neighborhood search algorithm HFS. And in the right figure, as you can see, the orange line gets stuck in the middle, and this is exactly because HFS sometimes gets stuck in the wrong local minimum, as I described in the previous slide. Based on what we have learned from BFM, we developed a new problem class called Corrupted Biospheromagnet, CBFM. Basically, CBFM is BFM with some noise. As you can see, instead of setting all j values to be -1, we set some of them to be positive 0.2, and similarly, instead of setting all h values to be either 0 or -1, we set a few of them to be positive 1. The choice of these numbers are made such that the overall BFM structure is maintained but harder to be detected. As illustrated in the diagram, the energy landscape of CBFM looks similar to BFM in the sense that the all ones configuration are still around the global minimum, and the all -1s configuration. Then we tried to solve CBFM again with the 7 algorithms, and here are the results. Firstly, we observed that this problem is more challenging for complete search. In the plot, the purple line can only find the solution after a few seconds, and this is because we hide the structure of BFM. For local search, HFS, the orange line on the right, performs a little bit better than in BFM, but still it occasionally gets stuck in the local minimum because we maintain the overall structure of BFM. Finally, quantum annealing is the fastest among these 7 algorithms for CBFM, as shown by the green line. This fact shows that quantum annealing can detect the solution structure quickly, even though it has become harder for complete search. And we think this could be explained by the non-classical behavior of quantum. In conclusion, we designed an optimization task called Corrupted Biospheromagnet and showed that quantum annealing is able to identify the solution structure of this problem quickly so that it becomes the fastest in our benchmark. Since I only have limited time in this talk, I've skipped quite a few interesting topics that are covered in the paper. For example, we provide a brief introduction of quantum annealing, assuming little preliminary knowledge, which might be helpful to learn this concept. We also did an analysis of each algorithm in the benchmark to understand CBFM better. And we proposed a Hamming distance metric, and using this metric, we can clearly see how quantum annealing performs better in identifying the solution structure. At the end, we also tried a solver that combines quantum annealing and the classical solver for integer quadratic programming. So if you are interested, please check out our paper. That's all of my presentation. Thank you for your attention.
Oops, I lost it. So thanks, Yuchen, that was great. So we've got a question from Emmanuel. How hard would that be to encode a known problem, e.g. your choice of graph problem, with the Ising problem and this hardware?
Yeah, that's a good question. And actually, yeah, it can be very hard. So I think that's the problem our first talk is mainly dealing with. So yeah, you need to use usually you need to use one node in the hardware to represent using multiple nodes in the hardware to represent one node in your problem, and yeah, so that's basically a graph embedding problem, and it can be very hard.
If I may just make a small comment. So there is a paper, the last name's author is Lucas, that he goes around and translates a bunch of NP hard problems into this Ising/Cubo formalism. Now, one thing is translating them into Ising, and another thing is putting them into the machine, right? You saw my talk was basically dealing with this whole embedding process, which is as hard as actually solving the optimization problem. And then for each particular problem, you can play with the formulations. As the second speaker was showing us, he had a very nice formulation for his problem. So this is similar to, I don't know, CP or IP, where there is a lot of focus on the formulation. So you need to pull up some tricks to come up with a nice Ising formulation for this kind of problems. And I think that there is a lot in there. And if you want to get into this thing, what we as a community know from IP and CP can be not directly transferred, but at least used to come up with better formulations of these problems in the Ising formalism.
So just as a kind of general question, I mean, it's an annealing approach. So it can also presumably get stuck in local minima depending on the temperature gradient or however that works. Is that right?
That is, I mean, theoretically, what you have to, so the big claim here is that since you're you're using an actual physical representation of the annealing, hopefully you can also get some advantage from the whole gist around quantum annealing is that hopefully you can, some of those phenomena that can be explained through quantum mechanics, for example, tunneling through one of these potential mountains, so to say, is something that this machine would allow you. So you would have better chances to reach a global minimum compared to normal simulated annealing. There is some, let's say, convergence properties in the limit. So if you were able to execute this algorithm very, very slowly and at temperature equals 0, you're guaranteed to reach the optimal solution, right? So they try to implement this on a physical system. So it's not temperature 0, it's temperature 13 millikelvin, which is still pretty cold. And on top of that, then it's not infinitely slow, but they try to make it like it's slow enough, it's still fast compared with other approaches.
Yeah, I get the idea. Yuchen, I mean, it's always hitting the best value in all your experiments. Is that's just lucky, or that's really where it's going to be for a wider class of problems?
Yeah, so one reason for that is because we are like building problems in the hardware graph, so that's easier for the machine. yeah, but I think in the experiment we've tried, like usually at the end you will find the optimal solution, like it's just faster or slower. So we've seen problems that quantum annealer is actually bad at. So, but yeah, at the end it will, and in anyways, the problem itself is not that hard because we have those like hardware topology, and we only have those not too many variables. So yeah, in that sense, it's close. Yeah, I want to mention like one problem that's hard for both like classical and quantum, I guess, which is the like random, like just all random. So just say everything random in the range. So that will be both hard for quantum annealer and that classical solvers. Yeah.
All right, there's going to be a Q&A, but I'm afraid we had to wait until after the next session for your Q&A, but I think a lot of people will be interested to talk to you. Thanks very much for your talks.